Hello students, welcome. So today we are going to start competitive lecture about D and F block elements. So basically we discussed about the details mentioned in textbook. In competitive we are going to discuss about few detailed thing about D and F blocks. Especially we will discuss about the examples of different type of metals used in D and F block elements. Few of them are mentioned in textbook and we will discuss about few more examples which are not mentioned. So basically in these lectures we are going to discuss about different type of metals and their compounds. And along with that we will discuss about few points which are not mentioned properly in textbook. That means they are not mentioned in detail in textbook. So let's start. So first thing, formation of colored ion is mentioned in our textbook but not in detail. So let's check it with proper illustration and images. So as we can see, initially when we do not have any kind of field around the metal atoms or ions, we have 5 d orbitals having same amount of energy. Now when octahedral field is applied, then two different parts of the same d orbit will arise. 3 will be between the axis orbits and 2 will be on axis orbits. Now octahedral bonds are on axis bonds. That means all of the bonds are present on axis x, y and z. And similarly, two of the orbits of the d are also present on axis x square minus z square and dz square. So because of presence of ligand electrons on axis, these two on axis orbitals will feel higher repulsion, and because of higher repulsion from the ligand electron, their energies will increase. And because of distance from the ligand electrons, energies of between the axis orbits will decrease, and that's why we get two doubly degenerated orbitals. Now degenerated, that means same in energy. So we have doubly degenerated orbitals, that means two different energy levels for 5 different orbitals. 3 of them will be decrease their energy which are in between the axis, and 2 will increase their energy which are on axis orbitals. And now if electrons are present in any of these between the axis orbitals, then they can absorb the energy coming from the light radiation which falls in our visible light range. So they will absorb the specific energy from the given waves. So suppose we are applying white light, that means it has all the wavelengths, and distance between these two energy levels requires only, let's say, red color to jump from lower energy to higher energy. So it will absorb the red color from all the lights, and remaining color will be seen as the color of compound, because red is being absorbed by these electrons. That means red light will be filtered out from our light source, and remaining light will be color of our compound. For that we need either at least one electron in lower energy orbital. That means d1 electronic configuration is minimum requirement. If you have d0 electronic configuration, then we do not have any electron to absorb the energy, and that's why no color will be absorbed. So minimum we need d1 electronic configuration. That means at least one electron in either of lower energy orbitals. And second thing, we should keep in mind these electrons need to jump from lower energy to higher energy. So that means we need empty space in higher energy orbital. So in this case, higher energy orbital can hold up to 4 electrons. So 6 are present in bottom and 4 if all of them are fully filled, that means total 10 electrons. Then electrons are present to absorb the energy, but they are not able to jump from low to high energy because we do not have any empty space available to accept new electrons coming from the lower energy orbitals. So that means d10 electronic configurations are also not allowed. If we have d10 electronic configuration, then compound will be again colorless. In this case, we have electron to absorb the energy, but we do not have empty space available so that electron can jump. That's why it will not absorb the energy if we have d10 electronic configuration. So out of all the possibilities, we have two possibilities for the d orbital which gives colorless compound d0 and d10. Remaining d1 to 9, all of them can show colored compound. Now let's talk about the tetrahedral field. So as we can see, tetrahedral field splitting is opposite to the octahedral. In octahedral, we have between the axis orbitals lower in energy, and now they are in higher in energy. We have higher energy on axis orbitals, and now they are lower in energy. So opposite splitting will be observed. So why octahedral field is opposite to tetrahedral field, or in this case why we have opposite splitting? So reason for that is, let's say these are the axis of our orbitals, or our metal. Our metal is present at the center. If tetrahedral field is applied, that means tetrahedral bonds are between the axis bonds like this. Okay, we have four bonds and they are present between the axis, something like this. So on axis orbitals are away from these ligand orbitals or atoms or ions or molecules, and that's why they feel less repulsion. And between the axis orbitals are present between the axis, that means they are present here, and we have bonds closer to it, and that's why this between the axis orbitals will feel more repulsion, and due to the more repulsion their energies will increase, and due to the less repulsion on axis orbitals we have lower energy of these orbitals. And the remaining description will be same. We have d0 and d10 which do not have electrons or no space available to accept the electron. That's why these two will be colorless compound, and remaining 1 to 9 electronic configuration will be colored. And color of compound depends on the gap of these two orbitals. As the gap increases, we need more powerful electromagnetic radiation. That means red to blue shifting. Red color lights are, we can say that it is the least energy containing waves in all the visible light range. And blue or violet colored lights are strong lights. They have shorter wavelengths, that means higher energy value. And red color has longer wavelength, and that means lower energy, because wavelength and energy, they are inversely proportional. If wavelength increases, then energy decreases. If wavelength increases, then decreases, then energy increases. So they are inversely proportional. So higher gap between the two levels of same d orbital, more requirement of energy will be there. So higher gap, that means our electrons will absorb the energy from blue color region. Lower gap, that means electron will absorb the energy from red color region. And in between state, that means it will absorb in between wavelengths. And gap of these two wavelengths depends on field applied on it. If we have stronger ligands, then this gap will be more. If you have weaker ligands, then this gap will be less. Here data related to absorbance and transmissions are mentioned. So as we can see, if infrared light is absorbed, now infrared do not belongs to visible light range. That's why we can see the white colored compound. If it absorbs red color, then we can see blue green colored of compound. Orange absorbance, that means blue color. Yellow absorbance, indigo color. Yellow green, that means violet. Blue green to red, blue then orange color. If indigo is absorbed, then yellow color. Violet absorbs, that means yellow green. And if UV light is absorbed, again this is not in our visible light range, that means white color will be observed. Then we have formation of complex ions. The transition metal and their ions shows strong tendency to complex formations. And reason for that is these metals have empty orbitals which can accept the electron pairs coming from other elements or molecules or ions, usually electronegative element containing molecules or negative ions. By accepting the electron pairs from these type of elements, it can form coordinate covalent bonds. And these coordinate covalent bonds have variety of different shapes and different type of properties and many different type of utilities and formations. Whole unit is dedicated to this type of compound, coordinate complex compound. So here basic detail is mentioned. So lone pair will be accepted from the given example CONONH like neutral or certain negative ions F minus Cl minus Cn minus etc., and they will form complex compound. So square bracket represents if anything is present inside the square bracket, then it has coordinate covalent bonding. In given example, Cn minus will donate electron pairs in empty orbital of Fe, and we have coordinate covalent bond. Similarly, NH3 will donate in Cu, H2O in Y, CO in Ni, NH3 in CO, and F in Fe. So all of them will donate electron pairs in given metals and it will form complex compounds.